Hello and welcome to the Advent of Code 2021, day 20. The exercise today, I'm not doing it live because it took some time and also I'm not very satisfied with the solution. But I'm going to explain it because I think it's very interesting. So essentially we are given a grid of points where every point is 0 or 1. A dot represents the 0 and this sharp sign represents the presence of a value, a 1. And together with this initial image, this initial matrix of values, we are given a thing that the problem calls the algorithm, which is a string of 512 dots or sharp signs. So essentially a binary string of zeros and 1 represented as dots and sharp signs. The length of the string, 512, is not a random accident, this is a power of 2, because these bits represent every possible configuration of a grid of 9 bits. Since 9 bits can have 512 combinations, it's possible to map every possible value of a complete grid to a bit of the string. And that will tell us what will be in every step of the evolution of this matrix the value of a central point, which means that every time we take an image, we can calculate for every point based on the grid of 3 by 3 that surrounds that point, the next value that the point will have in the next image. So essentially this image will become something like this, for example. Why? Because for every value in this grid, we associate a 0 or 1 to the 9 cells that are around it, including the cell itself, and find what will be the future value. This is a very interesting problem because this is what is called Cellular Automaton. I will put a link in the description because it's a very interesting entity, and there is a lot of interesting stuff you can do with this. For example, you can generate a Sierpinski triangle, or you can implement the game of life of John Conway. All of this is encoded in the algorithm. So essentially the list of possible states that a cell and its immediate surrounding can have, and how that makes the cell evolve in the problem. And what the problem is asking us to do is given initial configuration and the algorithm, of course, calculate the evolution of the system for a given number of steps, and return the amount of cells that are on. So how we implemented it is actually quite simple. I start by parsing the input, creating a set of coordinates that are turned on. So the problem is assuming that we are on an infinite grid, so we have a finite amount of values in our grid, but of course we can always expand them, so the image can essentially grow in size after every step of the algorithm, and the algorithm is just a string of characters. At that point I can execute a function that I called enhance, because that's how the problem calls it. This enhance function generates a new image, which is the result, and then iterates over all the points. This enumerate points helper is simply an helper that gives me all the coordinates that are relevant. So doesn't matter if they are positive or negative, since the image can grow. I simply iterate over every possible coordinate that covers the image plus 1 of margin. Once I do, I get for every cell all the cells that are around it, including the cell itself, by iterating over a dictionary of offsets. So this offset dictionary contains all the 9 relative coordinates that we can have compared to a cell, associated with the decimal value of the binary digit that is given by the problem. So the problem states that every cell, for example, this is 1, this is the second, this is the third, every cell is a digit in a binary number, so 0, 0, 0, 1, 0, 0, and so on. And is asking us to simply map this binary number to the decimal equivalent, but this is equivalent to taking the sum of the powers of 2 associated with every of these 9 cells. So what I do is simply iterate over the offsets and take the sum of the values at which I found some cell. And at this point, once I do, I simply get the corresponding element in the algorithm, so I know if this current cell will have to be turned on or off at the next instance, and if it's on, the answer, so if the algorithm contains a sharp sign in that position, I add it to the image. And at this point, solution of part 1 is trivial because I simply have to run this operation twice and get back the length of the coordinates, so how many coordinates are turned on. And this works perfectly on the sample input because I can easily simulate, run, and see what happens. I needed some work to get some small things like indexes off by 1 or stuff like that, but after running a few times and seeing the result, I could easily implement the algorithm and have it work on the sample input. The input that the problem gives us, however, has a very evil difference, which is this. This character changes everything. This first character, this first line is the algorithm, so this is essentially how the system has to evolve. This first character is very important because it's what happens when a cell is empty and all the surrounding cells are empty too. Which means that when you apply this algorithm to a given matrix, you will have every point of the matrix, which is infinite, I remind you, turning on, which means that you will have an infinite matrix of points that are turned on. Of course, you cannot handle really an infinite matrix, so we need some way to represent it. And this is where things get very complicated, because my initial approach was to create a flag, a boolean flag, which tells me whether the area outside the bounds of the matrix is to be considered completely turned on or completely turned off. So when I try to calculate the evolution of the system, I have a background on flag, and when I'm looking at for the cells around the given cell that I have to evaluate, I check whether the background is on and whether the cells that I'm checking are actually outside the bound, and if they are, I consider them turned on. So essentially I sort of virtualize the whole space of the grid that is outside the bound, so I do not have to represent infinite turned on cells, because that's of course impossible. And another thing I do is when I finished calculating the whole thing, I also calculate whether the background will be on or off based on the content of the algorithm. So I say that if the algorithm at position 0 has a sharp sign, it means I'm affected by this, and at the next iteration the background will be on, otherwise it will be off. Actually, the otherwise off should depend on the last element of the grid, which does the opposite. It tells me what to do when the grid is completely turned on. So basically it makes the background flash. That's what I implemented, and the logic I think is correct in general, but there must be some error, because the solution that this code generates, if I use the background on trick, is simply wrong. But this works on the sample problem, and this works on every problem that I crafted by hand to check the results, so there must be some error that I cannot see. And usually what I will do here is to create some visualization, see the problem step by step, write test, separate the method, the functions, and write tests for each one of them. Of course, here we are applying it to a toy problem. We do not really care. We don't have money involved, so I'm simply keeping as is and using a separate solution, which is brutal but effective. And the solution is simple. I know that at every step, whatever I do, whatever pixel I change, will have an effect only on the 8 steps, on the 8 elements that are around it. Which means that every error I introduce in the original matrix, in the original grid, will have an effect only expanding of a radius of 1 at every step. So what I do is I simply create two functions that I call the dump padding and dump truncation. Dump padding takes the edges of the current area and adds 2 elements, so turns on 2 to lights in the grid that are much outside the area that is actually interested by the problem. So you can imagine that here we create a huge grid, much bigger than this. We leave this image inside the grid, and then we also add some points that are much far away, just to force the whole algorithm to consider the whole grid, the expanded one. So essentially we are padding the grid with empty data, so that the border, which is going to be affected by the infinite grid problem, will be far away and will not affect the actual content of the grid in the time that the problem asks. So if the problem asks us to simulate 50 steps, we can just create a grid of, we can just create fake elements at 100 or more steps. Just to be sure I did 400. It's not necessary. I did 200. So more than enough to solve the problem. Of course, when I have to count the sides of the image at the end, I have to remove this stuff that I created. So I have a dump padding, which simply adds fake elements to extend the grid, and I have truncation does the opposite. So it takes the coordinates and reduces the range by the padding range, which is just the amount of values that I add, and ignores everything that is in this edge. So I simply pad, apply my logic, and truncate. And this works, and this is how I solve the problem. It's not nice, but it works, which is the most important thing. It's also not very slow in the end. It takes a few seconds to solve everything. Part 1 and part 2 are exactly the same. Part 1 is asking us to calculate the amount of pixels that are turned on after 2 steps, and part 2 the same after 50 steps. And so that was exactly it. Thank you for watching, and see you for the next problem. Bye!